is from engineering mechanics. Well, two men support a uniform horizontal beam at its ends. Okay, so here you have a horizontal beam at its end. Two men are supporting. Okay, so this is the weight of the beam. So when they are supporting each, then the forces exerted by the beam, the force which the beam exerts is these R's, okay, on each beam, and 2R is mg, R is mg by 2, or mg by 2 is the force that falls on each of the man. Let's say the force on the man is this R, and force on this man is this R. Okay, this was the free body diagram for the beam, and based on the beam we got the force exerted on each is mg by 2. Now what is given is that if one of the man suddenly leaves or go, how much will the force exerted? Let's say the man on the right suddenly moves up and you have only this support. So when it suddenly moves up, just that when he moves up, the free body diagram is like this. FPD, this is the force exerted now R1. These are just the forces. And now what happens to the body? Now the body is not in static. Now when the force suddenly goes, there is an unbalanced torque or unbalanced movement about the left man, which is mg into basically L by 2. This is L by 2. So now because of this unbalanced movement, the body is not in static equilibrium. It is, so initially it was in static equilibrium when both were supporting. Now here the motion is there, and it tries to rotate about. So this is the free body diagram, and now there is an unbalanced movement about the left man, about the point at which the left man is supporting the beam. Okay, so the mg into L by 2 is the net movement that adds, and because of this there is a dynamic motion and the body tends to rotate about. So at that point you can consider the body to be rotating about the left man, and so it is in motion, and it's like a fixed axis rotation about the man's contact point. The beam tries to rotate, so I naught into alpha is the rotational inertia. So we'll apply sigma moment. So now because it's in dynamic, so we can apply, because it's in dynamic, so sigma Fy is ma, so Cg is here, so may of Cg. So that is your basic Newton's law, and moment about O, the fixed axis rotation point, is I naught alpha. So these two equations. Now horizontally you don't have forces, otherwise we would have written the horizontal forces as well. So these three. Now first equation basically it's 0 is equal to 0. Now the second equation, which is sigma Fy is mass into Ag into Cy. Now sigma Fy, you have only the upward forces R1 minus mg. Okay, now the acceleration of point A, C moves like this. Okay, so let's put downward forces positive because acceleration of C is downward. So mg downward forces minus R1 is equal to MAC. So this is one equation. The second equation, we apply moment about O. So moment, mg is producing clockwise moment, so mg into L by 2 is the moment about O. That is equal to I naught into alpha. Okay, I naught is mass moment of inertia of the rod about O, which is ml square by 3. Now this is something which comes from the derivation ml square by 3. About the center it's ml square by 12. About its end is ml square. So from this we get alpha, which is 3 by 2 L G. 3G by 2L is your alpha. Now as the body in this case is in rotation about O, which is your left man's shoulder point, or wherever the contact point is there. So as about O, so acceleration of point C can be written as R alpha, tangential acceleration, which is nothing but R is L by 2 into alpha, because C is a point which moves in a circle, right? C is just point which just moves in a circle, so AC is L by 2 alpha. So this is equation 2, this is equation 3. So from 2 and 3 I got AC as L by 2 into 3 by 2 GL. So I get 3G by 4 AC, which is 5, or equation number 4. Now using 4, because I need to find R1, so using 4 in 1, I get mg minus R1 as MAC, which is 3G by 4. So R1 as mg minus 3mg by 4, or mg by 4. So compared to your starting, which is mg by 2, now the reaction that on the man, which the man provides on the beam, or the beam based on Newton's third law. So this is R1 is the reaction provided by the man on the beam just when the other man goes, because it's in dynamic motion, it's not in static motion. So the force that comes on the man is also mg by 4, so it has decreased. This is a very good problem. I mean, it's just counterintuitive. I mean, it's not that okay, the other person goes, so the force that comes on the left person will be more. No, that's not, because the beam is in a state of rotation. Okay, it's not in static equilibrium. Okay, so when you consider all the entire mechanics, I mean, so these three equations you need to apply for those planar equations. And just understand one thing here. This was the free body diagram, this was the kinetic diagram which shows the inertia. So all the forces, all the moments on the free body diagram, all the rotational inertia on the right hand side, you just basically apply forces and moment balance equation, and that is how you. The only point here is the body tends to rotate about O, which is the shoulder point for the left man. So force has decreased by half. Now the force is mg by 4. Answer is C. Thank you. This is a very good problem. Thank you.